Yesterday, we worked with rate of change. Today, the second part of our lesson, we're still going to be working with rate of change, but we're going to be working with rate of change specifically on a graph. So when you put rate of change on a graph, we give it a different name. So rate of change on graph, we call the slope. So slope is really the same thing as rate of change. It's situational. When it's on a graph, we call it slope. When it's in a table or in a situation, we call it rate of change. So we already know from yesterday that the slope, also known as the rate of change, is the ratio of the vertical change over the horizontal change. So vertical, if you remember, is up and down, horizontal, side to side. So when we're working on a graph, the vertical change we measure up and down, well, the axis that runs up and down is the y-axis. So sometimes instead of vertical change, you'll hear people say change in y, because that's where we would measure the change up and down. When we're measuring the horizontal change, or the change side to side, well, the x-axis on a graph is what runs sideways, so we end up looking along the x-axis to measure the horizontal change. So instead of horizontal change, sometimes you'll hear people say change in x. So we're going to look at working with this with different types of graphs, and then we're also going to look at how could I still do the same calculation if I just had the points off the graph and the graph wasn't drawn. So the best way to explain this is to show you as we work through it. So we're going to jump in with our first example and talk a little bit about how this works and also add some things into our notes as we go. So our first example, we've got this graph. So we can figure out our rate of change or our slope really similar to how we were doing yesterday. So we can measure, so we've got our 2 points right here and right here. So when we measure the horizontal and the vertical change, we're measuring straight up and down and straight side to side. So if I go straight up, my vertical change is running right there. So that would be a change of 3. So my vertical change is going to be 3. And the horizontal change, side to side change, is a change of 1. So 3 over 1. Oops, meant to draw 1 there. 3 over 1, which we know 3 over 1 is just 3. So what I drew, you could kind of see, looks like a little triangle on there with the vertical change and the horizontal change drawn in. So that is actually called a slope triangle, because that looks like a little triangle and it's measuring or calculating the slope or the rate of change. So what I just labeled on there is called a slope triangle. Now that we know, so we know the rate of change or the slope for this graph is 3. But I want to look at, well, what if we didn't have the graph drawn out? What if we just had the points 0, 1, and 1, 4? In math, one way that we find how far apart things are is with subtraction. So if I had said, how far apart are 3 and 7, you probably would have done 7 minus 3 in your head and told me, well, they're 4 apart. So subtraction lets us find how far apart things are. So when we were looking at, I'm actually going to change colors here because it's going to make it a little easier for you to keep track of things. So we're going to do our vertical change in blue. When we were looking at our vertical change, which was 3, so we were measuring on the y-axis, well, that started at 1 and it ended at 4. So what I was looking at was these numbers right here. So another way to get the vertical change is to take the 2 y coordinates and to subtract them. 4 minus 1. I can do something really similar with the x. So the horizontal change, we measure that along the x-axis. So that goes from 0 on the x-axis to 1 on the x-axis, which means I can look at these two numbers because those are controlling the horizontal change. 1 minus 0 is 1. And then I still end up with 4 minus 1, which is 3. 1 minus 0 is 1. I get the same answer calculating it that way as I got by actually drawing and counting on the graph. So we're going to look at one more example, and then we're going to add a little bit of vocabulary in with this shortcut strategy where we were just subtracting. So our next graph. On your notes, you have some room to do this beside your graph. I'm going to have to work below the graph. As long as you're putting it near your graph on your notes, then you're fine. So our next graph, we've got 2 points marked right here. So our vertical change is straight up and down. So in this case, if we're starting with the point on the left, we have to go down. So we're going to have to go down that far and then go straight across. So if we measure that out, we end up having to go down 2. And if you count out how far across we're going, it is a total of 6. So that means if we do our change in y is 2 over 6. So in this case, you could divide this out. If you divided it out, you would get 0.3 repeating. If you don't want a repeating decimal, you could just leave it as a fraction. In fact, when we're working on graph, we actually usually prefer a simplified fraction. So when we're working with slope, we prefer simplified fractions over decimals, and you will learn why it's better to keep it as a fraction over the next few lessons. So use simplified fraction. So I can reduce that 2 over 6 down into a 1 over 3, and I can leave that and have that be my slope rather than saying 0.3 repeating. So that is my slope. Now, let's try the shortcut way of doing this. So our coordinates, if we pull them off the graph, were -3, 3, and 3, 1. So to get the vertical change, the up and down change, that's being controlled by the y coordinates, which is the 3 and the 1. So I can do 3 minus 1, which is 2, to get that. And then the side-to-side change, that is being controlled by the x coordinates. So -3 minus 3 is -6. Now, we're about to realize something. We actually need to add something into our answer so that our answer is correct, because you might be noticing, wait a minute, -6. So yesterday we learned that if the line goes down, the rate of change is negative. So our answer, we got 1/3, but we have to remember to put a negative on that. It actually is -1/3 because the line is going down. So negative, or 2 over -6, a positive divided by a negative is a negative, but rather than literally dividing 2 by 6 and getting 0.3 repeating, again, we can just leave it as a reduced fraction, -1/3. So we get the same answer either way. Now, we're going to call a timeout for just a minute and talk about the subtracting shortcut before we look at our last 2 problems. So basically what we're doing is we're subtracting the y coordinates to get the vertical change or the change in y, and we're subtracting the x coordinates to get the horizontal change or the change in x. So if we wanted to write a little formula for the subtraction calculation that we're doing, what we're really doing, if we want to look at the coordinates instead of drawing it on the graph, is we're doing y coordinate minus the other y coordinate, and then the x coordinate minus the other x coordinate. But if you write that out, that gets really confusing because those 2 y's look the same and the 2 x's look the same, even though they're from 2 different coordinates. So if we have 2 different coordinates that we are subtracting, kind of like we did in our 2 examples, so that we could tell them apart, we put what's called a subscript. So a subscript is just a label, and we put a label on the bottom. So what we do is we put a little 1 down here, and that just tells me that that's the x and the y from the first coordinate. That's why we're putting a 1 there. And then we could come along to the second coordinate. We could put a little 2 down here. And all that does is that tells me is that's the x and y from the second coordinate. So now, if I'm looking at, both of the y's, the y from the first coordinate and the y from the second coordinate, I could tell them apart and tell which is which. So we basically want to say, take the y from one coordinate and subtract it with the y from the other coordinate, and then same thing with the x's. So that is basically our calculation we're doing. So this calculation is called the slope formula because it calculates slope or rate of change. So all it is just this subtraction calculation that we were doing right there and right there. So that's the slope formula. So rather than drawing it on the graph, you could also just take the coordinates and subtract that way. Another question that some people ask me that I get a lot when we're working with that. They say, well, does it matter which way we subtract? And the answer is no, as long as whatever way you subtract, you keep subtracting. So like on the first problem, we went from the right to the left coordinate, 4 minus 1, and then the same direction again. I could do that the other way around. I could do 1 minus 4, which is negative 3, and then 0 minus 1, which is negative 1, and a negative divided by a negative is a positive. Negative 3 divided by negative 1 is still 3. So I get the same answer either way. So it doesn't matter which order you subtract, as long as whichever direction you go with the y's, you keep going that same direction with the x's. You don't want to change your mind midway through. So that's a question I get a lot from people. So we know that if the line goes up, the rate of change or the slope is positive. We learned that yesterday. And if the line goes down, the rate of change or the slope is negative. What we haven't seen yet is two other directions that a line can go on a graph. The line can go up, the line can go down. The line could also be flat, or it could be straight up and down. Those are also possible directions the line can run. So we're going to look at what happens with our slope or our rate of change with a perfectly horizontal and a perfectly vertical line. So we know that on a graph or with coordinates, I'll show you both ways, just so you can see both ways. We want to do change in y over change in x. So on this graph, our 2 points from here to here, our change in y is 5, which we can also get by doing that point should actually be right there, I'm realizing. Or nope. Sorry about that. Typo. So that's actually our change in x, I'm sorry. So our change in x side to side, we'll change that to our x color just so it's consistent, we don't get confused. So our change in x side to side is changing by 5. So that's going to be the bottom number on our graph. We could also get that by subtracting. So negative 3 minus 2 is, and it's actually negative 5 if you go that way. So now where this gets a little tricky is that there is no up and down space between our points. So our points are kind of in the same place. So our vertical change, it's not changing. Our vertical change is 0. And if you try and subtract the coordinates, you can see that. You have to be careful because you have a negative. So negative 3 minus the other one is negative 3. Well, negative 3 minus negative 3 is 0. So if you look at that fraction and you think about dividing that, so if you think 0/5, well, 0/5 is just 0. It's nothing. So if you have a line that's perfectly horizontal, it's just running flat like that, it will always have a slope of 0. So eventually, you'll learn to recognize that, and you'll be able to see that line and not have to worry about calculating. And just automatically say, slope is 0. Now, if it's running the other way, this is where it gets a little bit interesting. So if we're running the other way, so now we do have a vertical change. So vertically, those points are 5 apart. So 3 minus negative 2. And remember, minus negative 2 is the same as plus positive 2 if you change your subtraction to adding. So that's going to give you an answer of 5. But now when we go to look at the side-to-side change, there is no side-to-side movement between those points. So our change in x, or our side-to-side horizontal change, is 0. It's not changing side-to-side. So you can see that here too. If you take these coordinates, 2 minus 2 is 0. So where this gets a little bit interesting, the last problem was 0/5, and that gave us 0. This is not the same thing as 5/0. So this does not also have an answer of 0. 0/5 and 5/0 are two different things. Two different things cannot have the same answer. So if 0/5, the last problem, is 0, then that means this problem can't equal 0. It has to equal something different. So to help you think about what's going on, we're going to do a little aside down here. So if we were to divide this out, because you were doing that yesterday, you were dividing out your rate of change to get a single number for your answer, we would have to do 5 divided by 0, which equals something. Now, we're going to think about fact families for a minute. When we were learning about integers, positive and negative numbers, we did a little bit with fact families. So if 5 divided by 0 equals some answer, then I should be able to work backwards and multiply. So that means if I were to use my fact families and work backwards, my answer times 0 should equal whatever I started with. But I immediately have a problem. We know that anything, no matter what number is here, that number, no matter what it is getting multiplied by 0. And any number times 0 is supposed to equal 0, not 5, which means this doesn't work. If you have ever tried this, or if you want to try it, see what happens, try doing 5 divided by 0 on your calculator. Your calculator will get angry at you, and it will give you an error message. This is why. In math, we can't divide by 0. Dividing by 0, when we look at the rest of the fact family, gives us statements that are mathematically false. So there is no number that I could put here that when I multiply it by 0, I will magically get 5. So this up and down graph, it exists. You can have a perfectly vertical line on a graph, but there's no number to represent that slope or that rate of change because we're kind of breaking the rules of math. So in math, there is a word that we use for something that doesn't have a number answer, and that word is undefined. So there's no defined or no definite answer, which is why we say undefined. So if you have a line that is running perfectly up and down, it will always have a slope or a rate of change that is undefined. So there are 4 different things that can happen with your rate of change or your slope on a graph. It can be positive if the line's going up, negative if the line's going down, 0 if the line is running straight across horizontal, or undefined if the line is running up and down perfectly. And there are also 2 different ways that you can calculate your slope. You can calculate it directly on the graph by drawing out the slope triangle and counting the squares to see what your vertical change and your horizontal change are. You can also use the slope formula, which is our trick of subtracting the y-coordinates to get the change in y, or the vertical change, and then subtracting the x-coordinates to get the change in x, or the horizontal change. So your notes at this point should look like mine, so you should have all of the same work filled in on your notes. So if you are missing any things that are on the screen, then I want you to write them down on your page so that you have all of that information too. And when yours looks like mine, then you can move on and try the practice assignment today. Your practice assignment today, you are going to have some graphs that are drawn out where you can literally count squares on the graph if you would like. You're also going to have some problems where you're just given the coordinates. And on the problems where you're just given the coordinates, you're going to have to use our subtraction trick.